All right, so the first part of this is just the timeline of kind of the history of the atomic model. And we're not going to spend a ton of time on that. You're not going to get questions about who discovered the proton, who discovered the neutron. But it is kind of important for us to just get an overview of the background to understand where we are now with the atomic model. Our last periodic trend we're going to talk about is electronegativity. And just like the previous two, our overall trend is up and to the right. So our highest electronegativities are over here in our non-metals. So electronegativity is the measure of the tendency of an atom to attract electrons. So it makes sense that it is a similar trend. It's not the same measurement as electron affinity, but it's going to be the exact same trend. Electronegativity is a calculated thing. It's not measured. And it's given a value between 0 and 4. And we're going to use electronegativity to talk about, get us into the concept of bonding and why different types of bonds are formed. The difference in electronegativity between two atoms is going to determine what type of bond forms between those two atoms. And I kind of think about this like tug of war. So if we have two people playing tug of war, and they have the exact same strength, then neither one of them is going to be able to pull that flag closer to them. And so it's going to stay right in the middle. And so that's going to be our pure covalent bond. So just equally shared bond. Neither one of them is pulling stronger, but it is being shared, so it is covalent. If we have kind of a middle difference in the electronegativity, now one person is stronger than the other, so I'm going to draw them some little muscles, and now they're going to pull the flag closer to them, and so that's going to be what we call a polar covalent bond, and we'll get more into that in just a minute. But then, if we have such a big difference in electronegativity that one just has such a higher electronegativity, so now it has like double muscles than the other one. Instead of pulling the flag closer to it, it just completely pulls the rope out of the other person's hand. So we think of that like ionic. The electronegativity is so different that we can no longer share these electrons. We just, one takes it away and the other loses it. So that would be ionic. So that leads us into our three types of chemical bonds. So chemical bonds are forces that hold atoms together. So that's what we're going to call intramolecular forces. We'll get into intermolecular forces next unit. But intra meaning within. So chemical bonds are between atoms. And we have three types. The first is an ionic bond. Ionic bonds are the force of attraction between oppositely charged anions and cations. So this is where we're really thinking about that Coulomb's law. This involves electron transfers. This isn't new to anyone. We're not sharing, like we just talked about in the previous slide. The electronegativities are so different that one of them is going to gain the electrons and the other is going to lose them, hence our cations and anions. They're going to form these crystalline structures. And that's because we've got these opposite charges that are attracted to one another. And so for every positive sodium, there's a negative chlorine. But there's nothing stopping this negative chlorine from being attracted to all the positive sodiums nearby, and vice versa. So that's why we get these crystal structures rather than individual molecules. So this also leads us to them being rigid and brittle. I mean, think about salt, like table salt. It makes crystals. If you hit it, it's going to break apart into pieces, so it's brittle. They've got really, really high melting and boiling points, because if you want to melt an ionic compound, you have to break apart all of these attractions within this crystal structure, which is going to take a lot of energy. When they're in their solid state, though, they cannot conduct electricity, because in order to conduct electricity, you need free charged particles. You need something to be able to conduct or pass along the electrical current. So when we're in our ionic solid, we cannot. However, if we put this into water, we know ionic compounds dissociate. Now we have free moving charged particles that can conduct electricity. So an important characteristic to know of ionic compounds is that they dissolve in water, and when they dissolve in water, they can conduct electricity, but they cannot conduct electricity as a solid. Some generalized rules for forming our ionic compounds is typically cations, so our metals forming positive ions, are going to lose all of their valence electrons. We're typically not going to have partial loss. So for example, if we're looking at magnesium, it has 2 valence electrons. It's going to lose both of those to make magnesium 2+. We do have some exceptions. So if we're looking at our later groups, even though they're in, like, let's say group 14, and we would say, oh, they have 14 valence electrons, not really. We got to take out the 10 for the d orbital. So we're going to take whatever group they're in minus 10. We also have the very bottom of those groups. We do have some partial loss of valence electrons. So something like lead can form a positive 2, even though it has greater than 2 valence electrons. Mercury is kind of funky. It can form mercury 2+ as well as a diatomic mercury 2+. And then our transition and intertransition metals, those are always going to lose their s electrons first. That's why we say, we mentioned this before, +2 is a good assumption for the charge of a transition metal, but some of them can lose a d or an f electron, and so that's where we can get these varying charges of like iron 2+ or iron 3+. And this goes all the way back to when we're naming compounds. That's why when we have transition metals, we have to use that Roman numeral to differentiate between which transition metal we're talking about, because they can form different charges. Or we don't have to use that for like group 1 or 2 because they only ever form one distinct charge. If we want to characterize different ionic compounds by their strength of their bonds, we don't really call it bond strength, we call it lattice energy. Lattice meaning that crystal structure. So it's the measure of the strength of the electrostatic attraction. So defined as the energy required to separate 1 mole of that solid into its gaseous ions. If you notice, the equation for calculating this looks exactly like Coulomb's law. So we have that the energy is going to be, again, directly proportional to the size of the charge, but it's going to be inversely proportional to the distance. So how can we apply that? Let's say we wanted to ask which one has the greater lattice energy, sodium chloride or calcium chloride. The one with the higher lattice energy is going to be calcium chloride, because of the calcium 2+ is going to have a higher charge, which is going to give us a greater lattice energy. Now, if we want to look at distance, let's compare maybe magnesium and calcium. So magnesium chloride versus calcium chloride. So both of them have that 2+, but because magnesium is smaller in size than calcium, magnesium chloride is going to have the greater lattice energy, because as the distance gets bigger, the energy is going to get lower. Moving on to covalent bonds. So while ionic bonds are transfers of electrons, covalent bonds are sharing of electrons. So we've got atoms with similar or identical electron affinities or similar identical electronegativities as well. These are going to form molecules. So now, instead of having those crystal structures, we have actual individualized molecules, so something like water. Next unit, we'll talk about intermolecular forces and how water molecules are attracted to one another. But within water, we do form these individualized molecules that don't bond to other molecules. So they have relatively low melting and boiling points, because in order to melt or boil them, you're just having to overcome the intermolecular forces, not in between the actual atoms. They tend to be liquids and gases at room temperature because of their lower melting and boiling points. They're pretty soft if they're solid. Most of them are insoluble in water. If they are nonpolar, that is, if they are polar, they would be soluble in water. And they are very poor conductors of electricity because we don't have any of those free flowing charged particles to pass the current along. So why do atoms form covalent bonds in the first place? So as atoms are moving towards each other, there's going to be different types of interactions. So as they get closer and closer, their electrons are going to repel each other and their protons are going to repel each other. But the electrons of one and the protons of the other would attract one another. So if we look over here at number 1, the atoms are too far apart to even be interacting with one another. But as they move closer together, they're going to get to a point where the energy is minimized. And at that point, then, they are more stable bonded than they are apart. And that's what we call our bond length. So it's exactly that distance that gives us the length of the bond. If they were to get any closer, it would take way too much energy to keep them that close. And so the bond length is that perfect distance where the energy is minimized, and so they're more stable together than they were apart. So going back to that idea of polar and nonpolar covalent bonds and electronegativity. So if we have the exact same atom, then of course they're going to share the electrons exactly equally, and so this is going to be a nonpolar bond. Neither one of them is going to be pulling the electrons strongly towards it because they have the exact same electronegativity, and so we can think of that like that flag being right in the middle. Neither one's pulling stronger. However, if we do have different ones, so like the example over here with hydrogen and chlorine, then the chlorine has a much higher electronegativity than hydrogen. So it is pulling the electrons more towards it, and so now we have this uneven distribution. So we can think of this like the flag being more towards the chlorine. And so we call that polar. It's going to be partially negative on this side and partially positive on that side. That's what these little S's indicate, slightly positive and slightly negative. It's not a full-on positive and negative charge. The only way to get that is for one to actually completely take the electron. And in that case, it would be ionic. We're still sharing, so there's no full positive and full negative, but there is a slight positive and a slight negative. And because there's a slight positive and a slight negative, we call this polar. So we talked about ionic bonds are characterized by their lattice energies, the strength of them. So covalent bonds, the actual bonds themselves, have a bond energy. And so the strength is measured by the energy required to break the bond. So of course, the stronger the bond, the more energy is needed to break it. And so we'll also see that stronger bonds are going to be shorter bonds. So let's compare these 3 carbon. So the carbon-carbon single bond is the longest compared to the double and the triple bond, but of course the triple bond is the strongest. So stronger bonds are shorter, weaker bonds are longer, and the stronger a bond is, the more energy it takes to break it, and so that's what we use as bond energy. You'll remember this from thermochemistry. We talked about bond energy because it was one way that we could calculate the delta H, the change in energy for a reaction, was by using bond energy, so this should be familiar to you. Bond energies are an average. If we look at the methane molecule, CH4, if we look at how much energy is required to break each carbon-hydrogen bond, so the first one would be the very first bond, let's say maybe this one, and then the second one, and then the third one, and then the fourth one. You'll notice the amount of energy actually goes down. So what we do then is we just take an average of these and we say that a carbon-hydrogen bond is 415 kilojoules per mole is how much it takes to break that bond. And so that's the bond energy that we would see in a table for a carbon-hydrogen bond. Our last type of bond is a metallic bond. I feel like the word bond here isn't really applicable, but we call it a metallic bond. And this is just really like a metal. So if you think of like a sheet of copper, we would call that a metallic bond. But really, it's just a bunch of copper nuclei arranged with their electrons delocalized or moving all around them. We sometimes refer to it as a sea of electrons. So they have metals have very low ionization energies. They don't pull on their electrons very tightly, and so it allows the electrons to kind of move around free flowing. This is what makes them such good conductors of heat and electricity, because we have those free flowing charged particles in the electrons, and when we add a current or heat, they can all kind of start flowing in the same direction and pass that current along. Because of these free-flowing electrons, they reflect light, and that's what makes metals shiny and lustrous. Because there's also all this space between them, they're very ductile and malleable. So remember when we said for the ionic compound, like a salt, when you hit it, it's going to break apart. Well, if you hit a sheet of metal, it's just going to bend and move, and you can shape it into things. And so they're very ductile and very malleable. So we're moving to everybody's favorite thing, Lewis structures. So a Lewis symbol is just for a singular atom, and it's only going to show valence electrons. So you'll notice we've got the Lewis symbols for, I guess this is the third row of the periodic table down here, and it's only showing the valence electrons. We always do kind of one per side. We can kind of think of each side of the atom as an orbital. So you're kind of going to do one per side before you double up, similarly to the way that you fill the orbitals in an orbital diagram. If we want to show ionic bonds in a Lewis structure, it's just a little bit different because we don't have physical sharing of electrons for those covalent bonds. So instead what we're going to do is we're going to put a bracket around the anion in order to kind of encompass all of the electrons that are around that anion. And then we put our charges. And so we know, like with sodium chloride, sodium has 1 valence electron, chlorine has 7. So that sodium is going to donate its 1 electron to chlorine. So that leaves sodium with no valence electrons left with a +1 charge. Chlorine has 8 now with a -1 charge. Same thing over here, except now we have like a +2 and a -2. If we have more than one, like in CaF2, we can just put a 2 outside of the bracket to indicate there are 2 fluorines. So ionic compounds, super simple. For covalent compounds, we're going to actually show the covalent bonds. If we see 2 electrons together, we call those a lone pair. There are 2 different ways that we can indicate bonds. We can either do actually 2 electrons, or we can draw a line to indicate that bond or those 2 shared electrons. I am always going to draw it this way. That's how I was taught. That's what I think makes more sense. I just think it looks neater. It easily differentiates between a bond and a lone pair, but you may see it either way. And the thing that you do have to remember is that that one single bond represents 2 shared electrons. So when you're counting up electrons or things like that, you've got to remember that a line represents 2 electrons, not just 1. So generally speaking, we're going to follow the octet rule, even though it's not perfect. Just like everything in chemistry, it's here's the rule and here's all the exceptions. So we get the term octet rule from the fact that our most stable elements on the periodic table are noble gases, and they have 8 valence electrons, which is what kind of makes them unreactive because they're stable, and so we call it the octet rule. Of course, there's some elements like hydrogen who can never have 8 because they only have 1 s orbital, and so its full octet is really only 2. So, but the idea is that all elements are working towards that full stable outer shell, whether that be 8 valence electrons or like 2 for hydrogen, we've got that full outer shell. So I think a lot of times what people struggle with Lewis structures is that they feel like it's like kind of just a free-for-all. Like I know I have these element symbols, and I know I've got some dots and lines, and I just don't know where to put them. So this kind of gives us a guideline for how to go about drawing a Lewis structure step by step. So if it's something super simple where when we draw them out like H2S, and we draw out like we've got two hydrogens with one, and we've got one single sulfur with 6 valence electrons, it's very easy to see that one hydrogen is going to be bound to each side of the sulfur to give it its complete octet. But if it's a little more complicated, we're going to follow these set of rules. And I'm going to try to do one. I'm going to do carbon dioxide as I go through these. And then on the next slide, there is lots more examples that go through these steps. So step number 1 is we're going to determine the total number of valence electrons that we need to account for. So for carbon dioxide, carbon has 6 valence electrons, and carbon has 4. Try that again. Carbon has 4 valence electrons, plus oxygen has 6, and there's 2 of them. So we need to account for a total of 16 electrons. If we're drawing the Lewis structure of an ion, we just need to take its charge into account. So if it has a positive charge, we would subtract that many electrons. If it's got a negative charge, we would just add that many electrons to the total. Step number 2, we're going to draw a skeleton structure. So we're going to put the central atom and just connect everything with a single bond. Typically, the central atom is going to be the one you have the least of, or it's going to be your less electronegative atom. Carbon is almost always going to be a center atom because it can make 4 total bonds. So we're going to put carbon, oxygen, and oxygen. So that's kind of what we call our skeleton structure. We just put our central atom with all the atoms bonded to it with a single bond. So now we're going to distribute other electrons as lone pairs on the outer atoms first to complete their octets. So you notice here I say except hydrogen. If hydrogen is bonded to something, it's already full because it can only have 2 total. So right now we have accounted for 1, 2, 3, 4 electrons. So 16 minus 4, I have 12 electrons left to include in my Lewis structure. So oxygen needs 1, 2, 3, 4, 5, 6 to go with these 2 to make a total of 8. And this oxygen needs 1, 2, 3, 4, 5, 6 to go along with its 2 to make a total of 8. Now, if I have any remaining electrons, I'm going to put those on the central atom. But we had 16 total electrons to account for. And right now in my Lewis structure, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I have already accounted for all of mine, so I'm not going to put any on the central atom. But I'm going to get to step 5 where it says rearrange for multiple bonds if necessary. So let's look at this. Our oxygens have their complete octets, but carbon over here is lonely. Carbon's like this little left out kid over here. All right. So it only has 4 valence electrons. So what I notice is I can move one lone pair from each oxygen down to make a double bond. And now everybody has a full octet. Oxygen has 1, 2, 3, 4, 5, 6, 7, 8. Carbon has 1, 2, 3, 4, 5, 6, 7, 8. And then this oxygen has 1, 2, 3, 4, 5, 6, 7, 8. So this would be my overall Lewis structure for carbon dioxide. So on this next slide, you can see that I use these 4 examples to go through all of the steps, counting up the total number of valence electrons, connecting them with a single bond for a skeleton structure, distributing all other electrons as lone pairs on the outer atoms, putting any remaining ones on the center atom, and rearranging if necessary to have multiple bonds to complete any octets. So some exceptions. There are a few molecules that have an odd number of electrons. And so obviously if we have an odd number of electrons, everything can't be in either lone pairs or shared in a bond. So we're going to have one unpaired electron, and that unpaired electron is called a free radical. This is not common, but if you see it, then you'll just know that you'll have one that's by itself. We do have some electron deficient molecules. So we already mentioned hydrogen. Beryllium and boron are two other ones. If you notice, boron only has 3 valence electrons, so it really only ever makes 3 bonds. So that means that boron's full with 6. We also have hypervalent molecules, and that's when a central atom can have more than 8 electrons. Now, you will notice that this does not ever show up until we have d orbitals present in order to expand that octet. So hypervalent molecules are never row 1 or 2. So never in rows 1 or 2 are you going to see. So like carbon is not going to expand its octet. Carbon doesn't have any d orbitals to put these extra expanded electrons in. Okay, so what if there are more than one way for us to draw a Lewis structure? So then we would have to pick which one is the best Lewis structure or the one that is more stable. And we do that with something called formal charge. So formal charge is defined as the hypothetical charge if we could redistribute the electrons in the bonds evenly between the atoms. So what I mean by that is, like, let's look at water. So let's say that we broke the bond apart and we distributed everything back equally. So then hydrogen would have its 1, oxygen would have 6, and hydrogen would have 1. All right. So then we kind of compare that to what it would be for a neutral molecule. So for this hydrogen example, or water, excuse me, hydrogen normally has 1 valence electron. Here it doesn't have any lone pairs and half of the bonding, so we already kind of broke that and gave 1 electron to each. So 1 minus 1 is 0, so the formal charge for hydrogen is 0. Oxygen normally has 6, minus the 4 that are in lone pairs here gives me 2, minus half the bonding electrons gives me a formal charge of 0. Hydrogen is the same over here as 0. It's kind of easier, instead of using this like formula right here, to just think about how many valence electrons would this atom normally have if it were a free atom, and then how many valence electrons is this atom having within the molecule. So if we look down here at the example below for iodine tetrachloride, so iodine would normally have 7 valence electrons. But here, iodine has 1, 2, 3, 4, 5, 6, 7, 8. So notice I counted 1 electron for the shared bond because the other one would go to the chlorines. So if iodine normally has 7 and here it's filling 8, that gives it a formal charge of -1. Chlorine, on the other hand, has 1, 2, 3, 4, 5, 6, 7, and that's the same for all 4 of the chlorines. Chlorine normally has 7, and so 7 minus 7 is 0. So the formal charge for iodine is -1. The formal charge for all the chlorines is 0. So let's do some practice. All right, so carbon normally has 4 valence electrons. Here it has 1, 2, 3, 4, 5. So the formal charge for this carbon is -1. Oxygen normally has 6 valence electrons. Here it has 1, 2, 3, 4, 5. So it has a +1 formal charge. Now notice that this whole molecule is neutral, and so my formal charges would need to add up to 0, which they do. Looking over here at the bromine molecule, chlorine normally has 7. 1, 2, 3, 4, 5, 6, 7. Has a formal charge of 0. Bromine normally has 7. 1, 2, 3, 4, 5, 6, 7. Formal charge of 0. And same for all these. Obviously, that adds up to 0. And then the nitrogen molecule down here, chlorine usually has 7. 1, 2, 3, 4, 5, 6, 7. So 0. Nitrogen normally has 5. 1, 2, 3, 4, 5. So all of those formal charges are 0. So you're really just comparing the valence electrons in neutral atom to the valence electrons in molecule. Okay, so what does all this mean? Why do we care about formal charge? So we can use the formal charge to predict which arrangement or which Lewis structure is better. So there's kind of a set of guidelines that we're going to want to follow. So the first is that anytime we can have all formal charges of 0, that is going to be the most stable and the most preferable. So if you look at this example down here, there are kind of 3 different ways that we could draw carbon dioxide. But these 2, when drawn, have formal charges on some of the atoms. The way we drew it earlier in the correct way has all formal charges of 0. So that is going to be preferable if at all possible. If it is not possible, so like the example down here of SCN, there's no way to draw it to get all 0 formal charges. So then we're going to pick the one with the closest to 0 or the least amount of formal charge possible. So this one is going to be the most preferable. Structures with adjacent formal charges are 0 or of opposite signs are preferable. So we don't want to have like a positive and a positive right next to each other if possible. And if we're choosing structures with similar formal charges, the structure with negative formal charge on the most electronegative atom is going to be preferable because that's going to be more stable. It's going to make more sense for something that has a higher electronegativity to have those extra electrons. If we want to look at a little bit more practice with just describing the formal charges, so down here, nitrogen normally has 5, but in this one has 1, 2, 3, 4, 5, 6. So that's what gives it the formal charge of -1. Carbon normally has 4, and here it has 4, so that gives it 0. Sulfur normally has 6, 1, 2, 3, 4, 5, 6, and that gives it 0. If we look at the second one, again, carbon normally has 4. Here it has 1, 2, 3, 4, 5, 6. So that's 2 extra electrons. So that gives it that -2. Nitrogen normally has 5. Here it has 1, 2, 3, 4. So that gives it that +1. And then sulfur normally has 6. 1, 2, 3, 4, 5, 6. So that gives it a formal charge of 0. So this is kind of a question you might be given on the test, is you would say, okay, which one of these drawings are preferable? So for the first one, we have dinitrogen monoxide. For the bottom, we have nitrogen dioxide. And it's saying, okay, which one's preferable? And so in order to determine which one's preferable, we've got to use our formal charges. So nitrogen normally has 5 valence electrons. Oxygen normally has 6. Here, nitrogen has 1, 2, 3, 4, 5, 6. So that's an extra electron on nitrogen, so it has a formal charge of -1. Here it has 1, 2, 3, 4. That's 1 less, so it has a formal charge of +1. And then oxygen has 1, 2, 3, 4, 5, 6. Normally has 6, so that's a formal charge of 0. On the right-hand side, again, nitrogen normally has 5. Here it has 1, 2, 3, 4, 5, 6. That's an extra one, so formal charge of -1. Oxygen normally has 6. Here it has 1, 2, 3, 4. That's a +2 formal charge. And then 1, 2, 3, 4, 5, 6. That's a -1. So for this one, the preferable charge, or excuse me, the preferable structure is the first one, because we have the lowest set of formal charges, -1, 1, 0, where here we have -1 +2 and -1. So we're always going to choose the lowest. From the bottom, again, nitrogen has 5 normally. Here it has 1, 2, 3, 4, 5, 6. Now, here we notice this is a charged ion, and so it has a -1 charge. So we need our formal charges to add up to our ion's charge. So -1 plus 1 minus 1 does add up to -1. Over here, 1, 2, 3, 4, 5, 6. So that's a formal charge of 0. 1, 2, 3, 4, 5. That's a formal charge of 0. 1, 2, 3, 4, 5, 6, 7. That's a formal charge of -1, which we have to have because it needs to add up to -1. So this has the most 0 formal charges. So that's going to be our preferable structure. Now, you'll notice that some molecules could be drawn equally in various ways, and we call that resonance. So down below, we're given carbon trioxide, which has a -2 charge, also known as the carbonate ion. And if we go to draw the carbonate ion, let's follow our set of steps from before. Carbon has 4 valence electrons, plus oxygen has 6, and there's 3 of those. Plus we have a -2 charge, so we need to add 2 more electrons. So altogether, that's 18, 19, 20. That's 24 electrons that I need to account for. So I'm going to do my skeleton structure first. Draw this a little shorter so we have more room. Okay, so now I'm taking care of 6. I still have 18 electrons to go, so I'm going to fill out my outer electrons on my outer atoms. So there's 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Okay, so that's all 24 electrons, but I notice that carbon doesn't have a full shell. So what I'm going to do is I'm going to move one of these down in order to make it a double bond. And when I make it that double bond, now everybody has a full octet. Now I'm going to check my formal charges because I got to make sure everything adds up to -2. So oxygen normally has 6, 1, 2, 3, 4, 5, 6. So that's a formal charge of 0. Carbon normally has 4, 1, 2, 3, 4, formal charge of 0. Oxygen normally has 6, 1, 2, 3, 4, 5, 6, 7. So there's -1, and here's -1. So that gives me my overall charge of -2. So now, where does this resonance come in? Resonance, not residence. Resonance come in. Well, I chose to make the double bond here between this carbon and oxygen. But there's no reason I couldn't have done it over here or over here. And so that's why you'll see down here we have all 3 of those options drawn with arrows in between. And what that is indicating is the resonance. Now, what chemists have figured out is that really a carbonate ion exists as a hybrid of all 3 of these at the same time. What do you mean by that? Instead of it being a carbon with 2 single bond oxygens and 1 double bond oxygen, what it really is a carbon with kind of 3 bonds that are in between a single and a double bond to the oxygen, which that's weird to draw. So what we draw instead is all 3 resonance structures, and we draw them out. But what that means is if we measure the bond length of the carbon-oxygen bond in a carbonate ion, it's going to be shorter than a single bond, but longer than a double. Which is what showed chemists that, okay, this is actually existing as a hybrid of all 3 of these structures at the same time, because all 3 bonds are equal in length and they're kind of in between a single and a double bond. So that's resonance structure. So first one we're going to do is this iodine tetrachloride with a positive 1 charge. So iodine has 7 valence electrons, chlorine has 7, times 4 is 28, plus 7, 35, but we got to subtract 1 electron for our plus 1 charge, so we have 34 total electrons that we need to account for. So I'm going to do my skeleton where I just connect all my outer atoms to my central atom. That's 8 electrons right there. So now I'm going to fill in my outer electrons first. So there's 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. Now I have 2 more electrons to account for in order to get to 34. I'm gonna put them on my inner atom. And so when we learn about Vesper in a minute, you'll learn that that has a specific shape, but iodine is just hypervalent at this moment. It has an expanded octet. So we can check our formal charges. So chlorine normally has 7. In all of these chlorines, it also has 7, so those all have formal charges of 0. Iodine normally has 7. Here it has 1, 2, 3, 4, 5, 6, which is a formal charge of plus 1, which is why this whole thing has a plus 1 charge. So all my other formal charges are 0, so that's the most stable Lewis structure for that. I don't need to change anything. All right, so sulfur tetrafluoride. Sulfur has 6 valence electrons, fluorine has 7. 28 plus 6 is again 34 electrons. So we have sulfur. Actually, I'll put this over here. So we have sulfur. I'm going to put them in their skeleton structure. That's 8 electrons, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. So I have 2 more and put them inside that atom in the middle. Check my formal charges. Fluorine normally has 7. Here it has 7, so that's a formal charge of 0. All of them have 7 around, so all of them have a formal charge of 0. And sulfur normally has 6. 1, 2, 3, 4, 5, 6. So that's also a formal charge of 0. So this is my complete Lewis structure. Now iodine trifluoride. So iodine has 7 again. Fluorine has 7. 21 plus 7 is I have 28 electrons I need to account for. So I'm first going to do my skeleton structure. So that's 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Oops, my pen keeps dying or losing its connection. Alright, so where was I? So 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So I need 4 more, and so I'm going to put them inside here on the iodine. And again, iodine is past row 2, and so it can have an expanded octet. So I'm going to check my formal charges, and fluorine normally has 7. On all of these it has 7, so its formal charge is 0. Iodine normally has 7. 1, 2, 3, 4, 5, 6, 7, so that's also a formal charge of 0. So that's my final Lewis structure. Once we talk about Vesper, we'll kind of redistribute these into their actual geometric shape, but for now, this is good enough. Now we've got sulfur dioxide. Sulfur has 6 valence electrons. Oxygen also has 6 valence electrons. So we have 6 and 6 times 2, so we have a total of 18 electrons that we need to account for. We're going to put sulfur in the middle. We're going to connect it to oxygen. So there's our skeleton structure. We have 14 more electrons to account for, so I'm going to fill in my outer ones first. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So we need 2 more. electrons, and so we're going to put them there on sulfur. So I can either check my formal charges, or I can just already see that sulfur does not have a full octet. So I'm going to put one of my lone pairs from oxygen down into a double bond. And now everybody has a full octet. I'm going to check my formal charges. Oxygen normally has 6 valence electrons. Here it has 1, 2, 3, 4, 5, 6 as well, so formal charge of 0. Sulfur normally has 6. 1, 2, 3, 4, 5. Here it has 5, so plus 1. 1, 2, 3, 4, 5, 6, 7, minus 1, which in total adds up to 0, which is our neutral. There's no other way to adjust this to get all formal charges of 0. What we can do, though, is there's no reason why we couldn't have moved the lone pair from the oxygen that's to the right of the sulfur. And so that tells me that there is resonance structure. So the other structure of this would be to do the double bond on the right-hand side. And so in reality, sulfur dioxide is kind of a hybrid of these two. So it's a sulfur with 2 oxygens that has a bond between them that's kind of in between a double and a single bond.